Hey guys, welcome to our lesson for section 8.1. Before we dive into the kind of note section of this, I want to kind of talk about some general things real quick about triangles. So, up until this point in the term, all the triangles we've dealt with and done our trig functions on have been right triangles. In other words, some triangle that has a right angle. That is really terrible, so terrible so that the computer didn't even think it was a triangle. There you go. Something that has a right triangle, okay, a right angle. Now, we are wanting to expand our world and not only be able to deal with right triangles, we want to be able to deal with any other triangles and all other triangles. So if it's not a right triangle, we call it an oblique triangle. And so an example of an oblique triangle, that's still pretty much a right triangle. It's oddly difficult to draw an oblique triangle sometimes when you're not thinking about it. There we go. An oblique triangle. Right? And these have that standard labeling, right? Where we label our vertices A, B, C. Our angles are labeled alpha, beta, gamma. Let's do better. Gamma's got a little bit of a loop on the bottom. And our side lengths are little a, little b, little c. Now, since this is an oblique triangle and not a right triangle, we can no longer apply the Pythagorean theorem, right? And if you remember, right, that was A, B, C on those sides. That was our a squared plus b squared equals c squared. Can't do that anymore, okay? So that only applies to right triangles. Now, I want to talk about something that is going to come up in this section called solving a triangle. To solve a triangle simply means to find all values of the angles and side lengths. Okay, so there were 6, right? If we look back over here, there's little a, little b, little c for our side lengths, and then angle measures alpha, beta, and gamma. Okay. When we are trying to solve a triangle, okay, we have a few possible cases with the information we're given. We pretty much always have to be given at least 3 things, and what those 3 things are kind of important. Okay, so we could be given side, side, side. Okay, so we're given all 3 sides. If we are given all 3 sides, this right here, come on, go away. This, we say it determines a unique triangle. There is only one triangle that will have those same exact 3 side measures. Pretty easy. Another one we could be given is side angle side. Okay. If we're given side angle side, okay, this means that we are given the lengths of 2 of the sides and we are given the angle between them. Okay. This also determines a unique triangle. Okay. Just a second. Okay, another possibility is we could be given angle, side, or we could be given angle, side, angle. And so this is kind of similar to side and side, right? Side and side, we're given the sides, 2 sides with the angle in between. Angle, side means we are given 2 angles and then a side coming off of one of them, not the side between them. Or angle, side, angle, we're given two angles and the side length between them. Both of these situations determine a unique triangle. Okay. Now, the other possible case is side, side, angle. Okay, so we have two sides are given and an angle opposite one of those two. This does not always determine a unique triangle. Does not always determine a unique triangle. Okay. Later on in our notes, we are going to go through a bunch of different cases of the side-side angle scenario and describe which ones yield a actual triangle, which one yield no triangle, and which one yields two triangles. So depending on what the values are for side-side angle, we could have no triangle, we could have one triangle, or we could even have two possible triangles. And so that's something that we're going to go over a little bit later in these notes. But before we do that, I want to now get into our actual lesson. So using the lovely law of sines. Okay. The way this is really built is it's built based off of a very simple idea of having some oblique triangle. And if you want to say that's over 90-degree angle, I'm going to tell you no, it's not. Okay. And what we do is we think, okay, we have our oblique triangle, and then we have this height h. Okay. I'm not going to worry about all of these angles. I'm just going to say this is alpha, this is beta, this here is A, this here is B. So what I have here is I really have one triangle, but I have it split into two if I imagine kind of making this height line a kind of hard break of these triangles. And if I think about it that way, then I can figure out the sine and the sine of alpha and the sine of beta using that height as a leg of a right triangle. And what I end up with is I end up with these two expressions. I get that the sine of alpha is equal to the height of the triangle over B, and sine of beta is the height of the triangle over A. And now both of these I can multiply by the denominator on that right-hand side to isolate h. And so what I end up with is B times the sine of alpha equals h, and A times the sine of beta equals h. The reason I want to do that is because now I have these two expressions both equal to the same thing, which means they must be equal. And that is this idea of the transitive law of equality, right? So if you say that A equals B and C also equals B, then it must be true that A equals C. Okay, so what we get is we get that B times the sine of alpha is equal to A times the sine of beta. And now what I can do is I'm going to divide both sides by AB. And what happens is on the right-hand side where I have B sine of alpha, the B's cancel. And on the left-hand side where I have A sine of beta, the A's cancel. And what I'm left with is sine of alpha over A equals sine of beta over B. And we could do an exactly similar idea if you think of kind of taking our triangle and you could rotate it if you wanted to visually, or just draw our H going in a different direction. If our H went, say, this way, we could do the same exact thing and find gamma. But I'm not worried about doing that, right? We can then just kind of extrapolate the same idea and be like, okay, I can see how we get sine of gamma over C equals these things. And then again, we get that equality. What's really nice here is if we notice that there is both the versions with the trig functions in the numerator and with the trig functions in the denominator. The reason that's really important is because it makes it so our calculations to solve things become really simple. We just take whatever the thing is that we're trying to solve for and put it in the numerator. Okay. And that way we have a known value in the denominator, we can multiply it out, and it makes our calculations a lot simpler. So let's do an example. This first example is going to be a nice example of angle, angle, side. So this is an angle, angle, side. Okay. So we're told to solve the triangle where we're given alpha is equal to 110 degrees, gamma is equal to 30 degrees, and side C is equal to 3. It's really nice and useful to get some sort of a drawing of whatever you're dealing with. And so by no means is this to scale, but it does work for what we need it. Let's say this here is our gamma, which is equal to our 30 degrees. This is our alpha, 110 degrees. And then this is our side C, which is equal to 3. So what I need to find is I need to calculate beta here. I need to calculate the value of A, and I need to calculate the value of B. And I can do all of that using one nice quick fact and using the law of sines. So the next quick fact I'm going to use to help me do this is I'm going to use a quick fact that the sum of the angles of a triangle is equal to 180 degrees. All right, so that means that alpha plus beta plus gamma equals 180 degrees. So what I can do is I can very quickly go, okay, cool. So for this problem, it means that beta is 180 degrees minus 110 degrees minus 30 degrees. We get that beta equals 40 degrees. All right. We have one of our three things needed to find. We have it found. So now we want to use our law of sines to find A and B. Since those are the things we're trying to find, we want to use the versions of the law of sine where the side lengths are on top. Okay. Again, that just makes our calculations a lot easier, and you're going to see that here. Now, I only know side C, so I have to use angle gamma. Okay, so that means I have to set it up where I get the equation 3 over sine of gamma. We'll actually put that in there. Sine of 30 degrees equals A over sine of 110 degrees. Now, the reason why this is nice is because now to get A by itself, all I have to do is I multiply both sides of the equation by sine of 110 degrees. Okay, these cancel out. I'm left with A is exactly equal to 3 sine of 110 degrees divided by sine of 30 degrees. And A is approximately equal to 5.64. So I know beta, I know A. All that's left to find is the value for B. Now, if you're looking at this, you're like, I could totally say, okay, cool. I could use A over sine of alpha equals B over sine of beta. But the problem is we don't have we have an exact form of A, but it's not a nice exact form. It's 3 sine of 110 degrees over sine of 30 degrees. I would much rather just use C, which is equal to 3. So I'm going to continue to use side C and gamma to find my beta, or to find my B. And so I get a very exact similar equation to what we had to find A, where I have 3 over sine of 30 degrees. And this time, instead of A, we have B. Instead of 110 degrees, we have 40. And I solve it in the exact same way. I multiply by sine of 40 degrees on both sides. These cancel out. We get 3 sine of 40 degrees over sine of 30 degrees equals B. And that means B is approximately 3.86. So if you're somebody who likes to kind of finalize your answers and stuff like that, that's a really great thing to do. I appreciate it as your instructor who's doing grading and things like that on tests. And we could simply say, okay, beta is 40 degrees. A is approximately 5.64. And B is approximately 3.86. And then square it, highlight it, whatever you want to do. And that's it. So this is really the idea behind law of sines, is identifying kind of if you have a unique triangle or not is kind of an important thing to do. And we're going to talk about some situations where that kind of comes into play. But on this example, we had angle, angle, side. Which falls into a unique triangle. So we don't have to worry about, is this a triangle or not? Only side-side angle gives us a non-unique triangle. And so then we just plug in and solve. Let's do another example. Okay. This time we're going to do angle, side, angle. Okay. We have angle, side, angle. Again, we are given a case that gives a unique triangle created. So it's easy. Notice here it's saying B and C instead of beta and gamma. You may see some different things. One other thing I want to kind of talk about real quick with those angles. Standard labeling will give us angles of, I'm going to come back up here to this triangle that we standard labeled. Or standard labeling, we'll talk about alpha, beta, and gamma. We could also talk about these angles. We could say something like angle alpha, that's the same as if I have this little symbol and then A. And that's the same as if I have this little symbol and then say something like BAC or similarly CAB. All of these are referring to, so all of these are referring to this angle here. Okay. And so alpha is just our kind of standard labeling of the angle itself. Then this symbol right here, this kind of looks like an angle, is the symbol for angle. And so this is saying angle A. So it's the angle at A. This is saying the angle created from going from the point B to the point A to the point C, going from B to A to C. That's that angle. And this is just kind of doing the same thing, but instead of BA to C, it's C to A to B. So those are some different ways you may see angle come up. It's hopefully something you maybe covered in a geometry class in high school. So I wanted to cover that right now with you guys just to make sure we're all on the same page. Now, looking at this example here, we have angle, side, angle. We're given angle B equals to 23 degrees, angle C equals 72 degrees, and side A, which is the side between angles B and C, is equal to 4. So let's draw what this triangle may look like. Like it kind of looking a little longer. You know what? I'm going to make it a little bigger. Okay, I'm fine. So this right here, so we'll say this is A, B, C. So that means this right here is our side A, which we know is equal to 4. This is our angle C, which we know is equal to 72 degrees. And this is our angle B, which is equal to 23 degrees. So doing the exact same thing as we did on the previous problem, we know that angle A, let me do this here. We know that angle A is equal to 180 degrees minus 72 degrees minus 23 degrees. And we get very simply that angle A is 85 degrees. Okay. So angle A 85 degrees. So to find sides C and B, we do the exact same thing we did in the previous problem. Again, since we're trying to find our side lengths, we are going to use the system where we have the law of sines, where we have the sides in the numerator. So we'll say we have B over sine of 23 degrees equals 4 over sine of 85 degrees. Now I'm going to spare you some details, and we're just going to jump. Say that B is equal to 4 sine of 23 degrees over sine of 85 degrees. And then using our calculator, we get that is approximately equal to 1.57. Quick note, I didn't make it before, but make sure your calculator is in the correct mode. So if you're not getting these values I got, so in like example 1, if you're not getting the 5.64, the 3.86, make sure your calculator is in degree mode. Notice all of these angles so far have been in degree measure, not radians. So make sure you're in the correct mode. And the only step I skipped here was writing out that I'm multiplying by sine of 23 degrees on each side. So hopefully that's okay with you guys. Do the same thing over here. We get C over sine of 72 degrees equals 4 over sine of 85 degrees. Again, I don't want to use side B and angle B or beta because I don't have a nice exact form of B, and I want to use the simpler version with 4. And so we get that C is equal to 4 sine of 72 degrees over sine of 85 degrees, which is approximately 3.82. And there we have it. We have our angle A, our side B, and our side C. Very nice and simple, straightforward, hopefully. Okay. Now, before we move on to our next example, I want to talk about this idea of bearings and travel direction and stuff like that. So when we talk about bearings or what bearing you're traveling at, okay, as long as a single angle is given and nothing more is given, we are always considering that as a angle measured rotating clockwise from due north. And I know that may seem kind of opposite. You're like, well, all we've talked about is positive angles are counterclockwise, and we start from essentially east. Why are we now going clockwise from north? Because it's how bearings are done. It's kind of, if you think about how you talk about direction, you always say northeast, southwest. You never say east, northwest, south. That's not how you remember your directions, most likely. I guess somebody could, but northeast, southwest is kind of how we talk about our directions. And so that's the same way we talk about our direction of travel. And so if we said something like, I'm traveling at 40 degrees. Okay, so if this is our north, east, southwest, 40 degrees would be this direction. Similarly, we'll do this in red. If I'm saying that I'm traveling at 200 degrees, okay, that puts us down here because this is 200 degrees. Okay. So let's see if we can't use that to help us out with example 3. Example 3 says that a ship is traveling west on Lake Superior. So that's nice. So it's traveling west on Lake Superior at 18 miles per hour. The bearing of Split Rock Lighthouse is 285 degrees. Then after 1 hour, the bearing of the lighthouse is 340 degrees. It asks us to find the distance between the ship and the lighthouse. Now you may be saying, okay, well, is that the distance at the beginning, at the end, right? Anytime we say find the distance between the ship and the lighthouse, we're assuming where the ship currently is, not where it was, right? So what we know is we have a lighthouse. I'm not drawing a lighthouse, sorry. And we have a ship that's traveling west. I have a ship traveling west. I'm going to trim that line down here in just a minute. Okay. Now, what I know is that at first, the lighthouse was at 285 degrees. So if I just think, I'm just going to draw this a little over here, right? I'm going 285 degrees. So 285, let's see here, all the way around to directly west is 270. So 285 is going to be something like this. So that's 285. That was really good. And then 340, well, if all the way around is 360, we're just shy of that. So let's do this in a different color. So it would be about here. So that would be about 340 degrees. So it means our first angle is kind of more westish, and our next angle is more northish. And you're like, cool, what does that tell me? What that tells me is that I started out here, right? I know I'm traveling west. I'm still haven't reached the lighthouse. I haven't like gone past where our lighthouse is. And so this is the triangle essentially that we're looking at. And what I know is that these angles can be calculated using what we know. So let's come back over here and let's focus on the 285. Like we said, to get to here would be 270 degrees. So if that's 270, how much further do I have to get up to our angle? Well, that means that this right here is 15 degrees. So this means this angle here is 15 degrees. Similarly, if I look over here, if this is 360, this right here is only 20. But that doesn't mean that this is an angle of 20. We can obviously, that's definitely not. But that angle is created from this. That's this angle, which from here to here we know is 90. Then we go 20 more. So that means it must be 110. Okay. So what we're doing is we're kind of using some of these angles we know to figure these out. It's similar to the idea of a reference angle. And so that's kind of what we're dealing with here. Okay. But then very simply, we can figure out this remaining angle by doing 110 or 180 minus 110 minus 15. And we get that this angle here is 55 degrees. So that's 180 minus 110 minus 15 equals 55. Okay. So we now know this. Now, all we have here is angle, angle, angle. But if we look back at our problem, we have that a ship is traveling west on Lake Superior at 18 miles per hour. The bearing of the Split Rock Lighthouse is 285 degrees. After 1 hour, the bearing of the lighthouse is 340 degrees. So how can I take that information and create I need to figure out some distance on here. And well, it comes from two pieces of information. That we are going 18 miles an hour, and we have traveled for 1 hour. So if we're going 18 miles an hour and we travel for an hour, that means we have driven, or in this case, boated, floated, whatever you want. I mean, it's still kind of driven, 18 miles. And so that's what we have. So we started here. So this is where we started. After an hour, this is where we're at. So this is where the ship currently is. We need to find this distance. How can I do that? Law of sines. Because I know this angle here and this side here, those compare together. So we get 18 for a sine of 55 degrees. And then what I need to find is this side here. So it means I need to use this angle here. It means that's equal to D over sine of 15 degrees. Now, that tells me very simply that D is equal to 18 sine of 15 degrees over sine of 55 degrees. Okay. Sorry, that was looking like a 3. There we go. And then again, we just use our calculator to approximate these values. We get that D is approximately 5.69 miles. Remember, we're dealing with miles here. So there's our answer. So after this 1 hour, so right where the ship is at this time when we've calculated these things instantaneously, the ship is 5.69 miles from the lighthouse. Okay, pretty cool, right? All right, now let's get into some fun things. It's kind of cool, it's kind of unique, but it is something that is kind of strange. Okay, so this is the side angle case. Okay, so this is that case that if you go back up to the very top of our screen here, this was the one that does not necessarily generate a unique angle. Okay, and so what we have to do is we have to consider a few different things. And so what I want to do is I want to get a general drawing drawn out, and then we can kind of adjust from there kind of how we would do this. So what we're given is we're given angle A, and side B. Okay, it doesn't really matter which kind of way they go, but the way I'm going to draw it just to kind of keep ourselves sane is like this. So this right here is our angle A. This is our side B. And this is our side A. What we also have to consider in this is this value here. So this is that height H. Now, the reason I've drawn A really short, you're like, that doesn't make a triangle. A is this length that we don't know what it is. So A could be this short, it could be longer, it could be, whatever it could be. And that is really what's going to be determined in these cases. Okay. Because we also have another possible case where our angle A is obtuse. Okay. And so if angle A is obtuse, that was a terrible straight line. We would get here's angle A, side B, and side A. We don't have to worry about height in this case, and you'll see why in a little bit. So those are two kind of possibilities depending on what angle A is. But let's go through our situations. Okay, so the case is that A is acute, and our little a is less than H. So that is exactly what we have drawn up here in this first diagram. A, B, A. So if we kind of think about if you were to build something like this and imagine putting A on a hinge, okay? It could swing around, and that's kind of how we're going to look at these different things. And so if we have A on a hinge, so it's hinged up right here, okay, it swings, kind of this is the path of its end, roughly. Notice that never would make a triangle. At best, it's going to be on top of B, in which case we have basically a straight line. And so if this is the case, we have no triangles. Say none. There are no possible triangles. The next case is that A is acute and A is greater than or equal to B. In this case, okay, what we have, A, B, we have some side A. Again, greater than or equal. if we, again, think of this hinged, right, and we kind of move it around, you only get one triangle right here. Okay, because when it comes down and falls on B, right, it's going to be on top of B. And if it's equal, then it's just a straight line here. It doesn't do anything. If it's greater than, it just extends past. So it doesn't really create another triangle ever. And so this, we get one possible triangle. Our next possibility is that A is acute, in that our little a is equal to H. Okay. So here, I can draw a straight line. Good enough. We have our A, we have our B, and our little a that's equal to H. If we swing this again, right, it never makes a triangle. Other than the one when it hits here, creating a right triangle. Again, we have one possible triangle. Now our next case is if A is acute and A is greater than our height, but less than side B. In this case, if we swing that's pretty terrible. There. If we swing this side, we actually end up with two possible triangles. Okay. So what happens is we kind of end up with one triangle where this angle here, this angle from between our sides A and B, is obtuse, and we end up with one where the angle between our A and B is acute. Okay. Almost there. We're almost done. We have two more to do. A is obtuse. And our little a is less than or equal to B. So we've got an obtuse value for A, for angle A. Here's B, here's little a. Because A is less than or equal to B, when we swing it around, we never get a triangle. So this is another situation where we have no possible triangles or none for possible triangles. Our last possibility is that A is obtuse and our little a is greater than B. In which case, if we run that angle around, we see we don't get anything other than that one. We only have one possible triangle. So those are our cases. This is something that I would definitely recommend having on a separate sheet of paper. Right, if you're creating a note sheet, have this on there so that you can come back to this and you are able to kind of use this as a quick reference when you are dealing with any time you have side-side angle. Okay, so if you're given two sides and an angle, it doesn't mean not two sides and angle, but two connecting sides and an angle opposite one of those two. Okay, so if you think about coming around this triangle, we have side, 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 angle. Okay, refer to this, check your cases, and go from there. Now you may be going like, well, how do I figure out H and stuff like that? And that's something that we'll deal with in a little bit. So right now I'm going to stop this video because I want to create two parts of this lecture, and we have a couple more examples to go. I want to give you some time to chew on this chart, think about it, and see you on the next video.